Hi, welcome to Physics 1.3 on linear motion. Remember how I said we were going to examine things in very deep detail. So today we're going to be looking at tables, graphs, descriptions, equations, all of it. So this is a multi-step approach. You'll start a problem with one given part and you have to do everything else. So you're going to have to do a written problem, a TUVE chart to go with the written problem, show the equation, the work, the answer, and the units, do a data table. Your data table needs to have a minimum of 2 points, max of 10. You have to do an XT graph, an X equals equation, a VT graph, and a V equals equation. And that's just today. Later on, we're going to add the AT graph and the A equals equation. But that's for next time. So, TUVE charts. Having a complete TUVE chart is almost always step one, okay? Especially if you're given a written problem. So, all your TUVE charts will actually start like this. You're going to look for distance, time, velocity terms. The units are going to hopefully be in meters, seconds, and meters per second. And then your variables will be x and x naught, t, and v. And we're going to add that a in later. The equation that you will either write the kinematic or solve the equation or rewrite the kinematic and evaluate the expression. So if you needed to solve 3x plus 2 is equal to 8, the evaluation of that would x is equal to 8 minus 2 divided by 3. And some of you are able to solve an equation and others are only able to evaluate. And that's okay. I'm going to give you the rewrites of the kinematics, the literal equations for your formula sheet for Kinematic 1 so that you can use those. We will be making a TUVE master chart together today. So a data table will consist of hopefully at least 5 points, and it will be time position data, but it's called a position time data table. From the data table, you can draw an XT graph, and the XT graph needs to have all 4 parts of a graph. It needs to have the axis labels with the units. It needs to have scales, and remember scales are what you're going to count by. It should have a title, and then obviously plot the points and draw that line of best fit, which these should all be lines. Your x equals equation will either be Kinematic Simple or Kinematic 2, those that are only x equals equations that we have. So if the graph is linear, it's going to be a Kinematic Simple where you'll replace the x naught and the v. If the graph is not linear, it will be a Kinematic 2 equation where you'll replace the x naught, the v naught, and the a. Your VT graph starts out looking like this. Notice it is still a 10 by 10 grid, but it's divided in the middle. Because remember that velocity could either be positive above the t-axis or negative below the t-axis. But again, it should have axis labels with units. It should have scales, what you're going to count by. It should have points and or a line. And the title is not really necessary here because the VT is going to go with the XT. The V equals equation will be the rewrite of will be Kinematic 1 since that's the only V equals equation we have. If the XT is linear, the V equals equation will simply be a number with no units attached because it's the equation of a line, a flat line. If the graph is not linear, it will be a V equals equation where you'll replace V naught and A. So graphs in general are used to show or diagram information visually. An XT or position time graph shows the object's location relative to the origin at a given time. The VT, or velocity time graph, shows an object's velocity at a given time. So xt graphs, the x is the vertical or dependent axis. The t is the horizontal or independent axis, because remember, time is the ultimate variable you cannot control. The origin, the corner, is always 0, 0. And in science, we don't have any breaks, any jumps. Your scale has to work. The VT graph, V is your vertical axis, T is your horizontal axis, and again, the origin, the corner, is always 0, 0 in science. So your equation for today is kinematic simple. This is the equation associated with linear constant velocity motion, where x is the object's final position, x naught is the object's initial position and the vertical intercept, v is the object's velocity and the slope of the line. That is vitally important. And t is time measured in seconds. Graphs are more than just representations. This is absolutely vital that you understand. The slope of an xt graph equals the velocity. The area of the rectangle formed under a VT graph is equal to the displacement, the x minus x naught, or the delta x. So when you are problem solving, you're going to be given any part of that multi-step process, and you have to complete all the other parts. Tables are very convenient here. So if you're given this example, a rectangular field is 100 meters by 50 meters. A man walks the perimeter of his field in 112.2 seconds. At what velocity did he walk? Well, our first step is to do a TUVE chart. You're given meters, seconds, and velocity. So filling in the TUVE chart now with values, your x naught is 0 because he starts in one spot. Your x is 300 because that would be the entire perimeter that he goes, his distance. His time is 112.2, and we're trying to find his velocity. So the equation that we need is kinematic simple, and we need the rewrite of velocity, which is x minus x naught divided by t. 300 divided by 112.2 is 2.67 meters per second. Then we need a data table, and this data table only has 2 points because it starts at 0, 0, a time of 0, position of 0, and it ends at 112.2 seconds and 300 meters. That's the data table. Then the xt graph is literally just a graph of that. The x equals equation is the equation of that graphed line. X is equal to 0 plus 2.67t. The v equals graph and the v equals equation. V equals graph is the graph of the velocity. Notice that the time scale does match. It is from counting by 20s, just like it was on the xt graph. And the equation for the VT graph is v is equal to 2.67. Hopefully, you're going to have a lot of practice today. Thanks for watching.